Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep. Let's try to recall what we were discussing the last time. So in the previous class, we were looking at how important the design of analog peripherals are in overall memory arrays. So as this picture very clearly indicates, there are two key subdivisions when you look at a memory chip. One is the actual array, which here we have marked out with a square array, and the other, which we have marked out in dotted lines, is the area which is occupied by the peripherals. If you recall, I had given a very simple example of food delivery apps. Generally, we would expect from the food delivery apps that the convenience fee that they charge should be much smaller compared to the price of the dish or the price of the food that we are ordering. The situation is quite similar here also. You would expect that the size of the peripherals, which is just used to access data efficiently, will be minimal compared to that of the memory array. So in today's class, we will see, is that really the case? And to understand that, we have to see what the memory footprint is for two elements. It will be due to the array, and what will govern the memory footprint of the array will be the individual cell area or the cell size of a individual bit. This, when implemented at array scale, will determine what will be the size of the array for a particular capacity. When we were studying the memory hierarchy, we saw that as we go down in the memory hierarchy and away from the CPU, the latencies suffer. However, what the benefit that we get is in terms of bit density. This is because the area consumed by the device which is storing a single bit of information shrinks drastically. This is what we see in this schematic as well. Now, since different technologies, whether it is SRAM, DRAM or NAND flash, will have different process technologies, in order to make a proper comparison, we should first indicate what is the smallest feature size of the corresponding technology. So if the smallest feature size of the corresponding technology is F, then what is the area in terms of F squared? Because F is linear dimensions, the area will be in terms of F squared. So in case of an SRAM cell, as you can see, the height of the cell is roughly 7.5 to 10 feature sizes, whereas the width of the cell is 20 to 30 times of the smallest feature size. This is because a single SRAM cell packs in 6 transistors. The multiplication between the height and the width will give you roughly 150 to 300 F squared. This is the case for SRAM. When you go to DRAM, of course, latencies increase substantially, but as you can see, the device becomes simpler in terms of cell area. Now, instead of having 6 transistors, you have only 1 transistor and 1 capacitor. Therefore, the DRAM design can fit within 3F multiplied by 2f, which is roughly 6f squared. How is the story when it comes to NAND flash? Please try to recall. The NAND flash is essentially one modified transistor. So even you have removed the capacitor which was there in DRAM. Therefore, single 2D NAND flash cell, which is storing just one bit of information, can hold this within just 2f and 2f sides, and therefore 4f squared. While we were studying the innovation trends in NAND flash technology, we saw that not only are you trying to reduce this value f and therefore reduce 4f squared or the cell area, you were also trying to do bit scaling. That means that within the same footprint or within the same NAND flash cell, you are trying to add more and more number of bits. As a result, the bit density was also improving. And this is what you see in this schematic. In a multi-level cell consisting of n bits, the area footprint or the array footprint per cell or per bit will become 4f squared by n. Things become even more interesting when you go to 3D NAND flash multi-level cells. This is because in a 3D NAND flash multi-level cell, you are not only scaling in terms of area, which is f, but also you are doing vertical scaling. In the same footprint of 2f and 2f, you are integrating several NAND flash cells or NAND flash floating gate transistors vertically. Therefore, the bit density further improves to 4f squared, which is the size of this cell, divided by n, which is the number of bits you are storing in each of the cells, divided by L, because now you are stacking L such cells within 4f squared areal density. So as we saw how there is a drastic improvement in the bit density and therefore the memory footprint of from the SRAM to the DRAM to the NAND flash and even 3D multi-level NAND flash. So intuitively, one may guess that the footprint of a NAND flash will be much better compared to the SRAM cell, and DRAM will be somewhere in between. But that is only part of the story. As we had seen in the previous slide, the other half or other portion of memory cell the entire footprint is also contributed by the cell area, which is from the peripheral circuitry. We have been discussing for quite few classes that the peripheral circuitry consists of digital elements such as the row and column decoder and analog elements such as the sense amplifier, the pre-charge circuitry, some buffers, the control and timing circuitry. The control and timing circuitry is critical because each read and write cycle has some sequence of events which also needs to be controlled by the memory controller. This area overhead also goes into the peripheral circuitry. Furthermore, there are some important elements called the level shifters. What are level shifters? Level shifters are these analog elements which convert the voltage between the memory peripheral circuitry to the actual array. Let me give the example of NAND flash. The peripheral circuitry in a NAND flash generally can work in the digital domain from 0 to 5 volts or 0 to 1 volt. However, for the NAND flash to operate successfully, the voltage that we apply at the gate is in the range of 0 to 20 volts. So you need some level shifters to do this changeover from 0 to 5 volts to 0 to 20 volts. This gives us an opportunity to define a new metric, which is memory array efficiency. Memory array efficiency is defined as the ratio between the area occupied by the array divided by the total area in the memory chip. As we know, the area in the chip will consist of both the array and the peripheral. If you want to represent it in percentage terms, you just have a multiplication factor by 100. Needless to say that higher is the area efficiency, lower is the cost per bit. Again, looking at your food delivery app, you would expect that the surcharge or the convenience fee, which is nothing but the peripheral over here in this example, should be much smaller compared to that of your food charge or your dish charge, which is nothing but your array area. So let us look at how the array efficiency looks like for SRAM, DRAM and NAND flash. To get an idea of the same, I have indicated or represented the memory footprint, memory floor plan of a typical processor. So as you can see, this is an octa-core processor consisting of 8 cores, 4 on either side. The interesting part to note is that the L3 cache, which is shared between all the 8 cores, consumes almost the same area as the 8 cores. Within the shared L3 cache, we see two regions. One region which looks fairly uniform, which I am pointing at. This is the area of the memory array. An equivalent area, as you can see, is consisting of some digital elements, which is the peripheral circuitry. So in case of shared L3 cache, which is an on-chip cache, it seems like that the area efficiency is very poor. It is only 40 to 50%. So the peripheral circuitry occupies almost half or even more than half of the entire chip area. And we have not even discussed the L1 and L2 cache, which is embedded within each core. Recall from our discussion that L1 and L2 cache is individual to each core, whereas the L3 cache is shared. Why are we willing to tolerate such poor array efficiency? This is because when we look at cache memories, the entire focus is on performance. The example when you talk about food delivery will be if you are extremely hungry. If you are extremely hungry and somebody tells you that I will charge you double or I'll charge you as much as the food, but I will give it to you within 5 minutes, you may be able to tolerate it. Similarly, your cores are also very hungry for data. Since the cores are very hungry for data, the focus on the caches is on performance, and therefore you are able to tolerate this poor array efficiency. However, that is not the case when you go to DRAM or NAND flash. On the right hand side, I have indicated the memory array for a NAND flash. As you can see, the 4 GB NAND flash occupies quite a large amount of area, and the peripheral circuitry is a small fraction, roughly 20 or 30% of the total area. In NAND flash, the area efficiency is roughly 70 to 80%, and in DRAM, it is roughly 60 to 70%. Why is the efficiency in DRAM slightly smaller? Due to two main reasons: that the bit density in NAND flash is slightly better, And also, the peripheral circuitry in DRAMs is slightly more complicated because you are facilitating random access in DRAM compared to sequential access in NAND flash. With this, we conclude our discussion about area efficiency and come to the last topic of this module. In the last topic of this module, we will try to look at design of a memory peripheral. So let us take our own example which we were discussing a few classes ago. How do we design a 32 megabit array with a word length of 32? What will be the values of the address bus, which is nothing but m plus n? Or in other words, how many bits should be feeding to the row decoder, and how many bits should go to the select lines of the column mux? Or in other words, what would be the size or what would be the number of bit lines and word lines? The first consideration to keep in mind is that since we had a square array, the number of bit lines and the number of word lines have to be identical. This is what is indicated in this particular equation. So the number of word lines is 2 to the power of n because the input to the row decoder is n. So there can be 2 to the power of n word lines which are indicated in red horizontal lines. And the number of bit lines will be k into 2 to the power of m. This is because the bit lines are divided into k pages, each having 2 to the power of m columns. So the total number of bit lines have to be k into 2 to the power of m. And since this is a square array, the number of bit lines have to be equal to the word lines. So k into 2 to the power of m should be equal to 2 to the power of n. Since k is 32 in our given case, we are working with an older generation of processor whose word length is 32. Remember, we discussed recently we have moved to 64 as the word length also. But in this example, let's consider k to be 32. So 32 is nothing but 2 to the power of 5. So the first equation, which comes from constraining the number of word lines to bit lines, because you are considering a square array, is m plus 5 is equal to n. This is the first equation. What would be the second consideration? Please try to recall. The second consideration will be the size of the memory array. The size of the memory array was nothing but the word line multiplied by bit line, or the number of word lines multiplied by the number of bit lines. This is because at the intersection of every word line and bit line is one memory cell. So the multiplication of word line and bit line will give you the size of the memory array, which in this case is 32 megabit. So word lines were 2 to the power of n, bit lines were k into 2 to the power of n. So the left hand side of the equation becomes 2 to the power of 5 plus m plus n, whereas 32 megabit can be written as 2 to the power of 25. So the second equation, which is coming from the size of the array, becomes m plus n is plus 5 becomes 25. If we solve equation 1 and equation 2 consistently, we see that the values for m and n is 7.5 and 12.5. Now this is a really big problem because you cannot decide or you cannot design row decoders and column muxes with non-integral values for m and n. So what could be the solution? So the solution is something that I would like you to just pause the video and think for a while. So the best solution that can come to the mind is the reason why we were getting these non-integral values is because the value on the right hand side of equation 2 was an odd number. If we would have made it an even number by considering word line into bit line as 16 megabit, just half of 32, we would have seen that equation 2 gets modified as 5 plus m plus n is 24, because now we have just taken half value of 32 megabit. So this value, which was odd, 25, now becomes even. Now if we solve equation 1, which is m plus 5 is equal to n, and 5 plus m plus n is equal to 24, we get a consistent solution of m is equal to 7 and n is equal to 12. This means that the total size of the address bus has to be at least 19. However, our target was to build a 32 megabit array. We have only successfully built a 16 megabit array. So the solution is, why don't we have two separate blocks of two 16 megabit arrays? And the free address bit can be now used to choose between the two blocks. As you know, one bit can choose between block 1 or block 2. A more generic representation of the next example is the so-called block level implementation. In block level implementation, what we essentially do is replicate one optimized block several times. In addition to having the address bits as m and n, where n goes to the address decoder and m goes to the column mux, we have b bits assigned to the block address. If b bits are assigned to the block address, we can understand that the total number of blocks that can be implemented is 2 to the power of b. So how does read or write access happening in this kind of architecture? It is very simple. The m plus n bits are supplied to each of the blocks address decoder or row decoder and column mux. So in essence, within all the blocks, the same word lines and bit lines are being selected. Each of them give out k bits of data. Which of the k bits of data is actually selected and asserted on the data bus is determined by the remaining b bits. The b bits indicate which block is giving out the relevant data. So if b was considered to be equal to 3, we can say 2 to the power of 3 is 8 blocks. And the digital combination of b bits will tell the k bits are coming out from which relevant block. What is the key advantage of implementing this block level design? The key advantage is that of modularization. What is the meaning of modularization? Suppose I have designed a 4 GB data memory array today. Tomorrow I want to scale it to 16 GB. Should I change all my peripheral and memory array design? No, that is not needed. Why don't I just copy paste 4 GB data cells so that we can have a modularized design? This will save me a lot of time and cost and effort in redesigning the new memory requirements, expanded memory requirements. So this is a very important aspect which is known as modularization. The second important aspect is, with block level design, you can have limited size of arrays. If we have limited size of arrays, we will have limited length of the word line and bit line. As we had discussed earlier, the size of the word line and bit line affect the read and write latencies. So if the word line and bit line are too long, the read write latencies suffer. So by having block level design, you can expand the memory while as your core unit or your fundamental unit remains small. And this is how you control read write latency. Final important advantage of having block level design is the concept of power management. As you know, there are two kinds of power consumption which happens in all computing systems. One is your static power, another is your dynamic power. The dynamic power is the power which gets consumed when there is switching of devices. Since clock is what is responsible for switching of devices, if we realize that some of the blocks are not in operation in the entire design, you can do clock gating. For example, at one given time, only block 2 is being used. So all blocks except block 2, the clock can be cut off. If the clock is cut off from all the other blocks, the switching dynamic power, which is nothing but CV squared by F, could be easily saved. In addition, we could also do power gating. What is the meaning of power gating? There is a context to power gating when we look at different kinds of memories. If we are dealing with a volatile memory, you cannot simply switch off the power supply to the array. So what do? You bring down the power supply to a small minimum value such that it is enough to hold on to the data. Whereas in a volatile or in a non-volatile scenario like NAND flash, you can completely switch off the rails to which are going to the array. Therefore, by using modularization, you can not only limit the array sizes, you can also do effective clock and power gating. With this, we conclude our module 2, and I hope you have got a fair bit of idea how using very intelligent memory array architecture, large scale memories are built. This is a good time to summarize what we discussed in module 2. First, we carried on with our understanding of memory hierarchy by looking at some practical examples from MacBook Air and from your Samsung Galaxy S20. We saw that memory hierarchy is always continuously changing. It is fluid and it is driven by innovation. Next, we did a deep dive into the commercial or economic aspects of the global semiconductor memory market, and we saw that the memory market is driven primarily by innovation. All companies are essentially trying to reduce the cell area and therefore optimize the cost per bit. We saw what are the different innovations which are happening for SRAMs, DRAMs and NAND flash. It was also interesting to note that the maximum growth in innovation, or even in terms of annualized growth, is happening in the new storage class memories, and therefore they are considered to be very important for the future. Finally, we looked at what is the importance of first memory array design, how we folded a rectangular array to a squarish array by employing the concept of a page, and how the associated memory peripherals also get modified. We also looked at the importance of analog peripherals such as pre-charge circuitry and sense amplifier, especially in the context of latency versus area trade-offs. Today, we looked at what is the definition of memory array efficiency, how it can change from technology. SRAM, DRAM and NAND flash have increasing memory array efficiency because of improved bit density. And finally, we looked at the importance of modularized block level design for expanded memory. Thank you. I hope this was a valuable module. In the next module, we will start a deep dive into individual memory elements, starting with the SRAM.